Previously, we have discussed how to determine the work done using an equation, and that's for situation where your force is constant and your displacement is in a straight line. Now we are going to move on to try to determine work done using a graphical approach. But for this approach, there's a bit more flexibility. You can use it to determine work done even if the force is a varying force. Okay, so now we are going to study work done by a varying force undergoing a straight line displacement. Okay, in your syllabus, they strictly say it's for constant work done by a constant force, even though it's graphical approach. They only limit you to constant force. But based on many mock exams that I have seen, many questions ask about varying force, even though the syllabus is constant force. So I'm still going to teach you work done by a varying force undergoing a straight line displacement. Okay, so I'm going to do a bit of flashback to chapter 3 first. I'm going to show you in chapter 3, impulse and momentum, we learned that impulse is actually equivalent to the area under the force time graph. Okay, if you see in chapter 3, I didn't put in the sigma, but it's actually, there's a sigma that means by it's actually a net force against time graph. So if we plot our net force against time graph, in chapter 3, most of the time, the net force is not constant with time. Let's say if you hit the baseball with a bat, you have to touch softly, hardly, then the ball leaves you. So the force we have to spike then goes to a 0. So usually in some kind of collision, right, the net force acting on an object is usually in a shape like this. But we know that if you are able to determine the area under this graph, then this area here will be representing the impulse. So you can use this equation to say that impulse is equivalent to the area under the ft graph. Well, this is integration. You might not have enough knowledge to understand what this equation means, but never mind, in SEM 2 you get more familiar with this kind of equation. Basically, you see integration, you know that means area under the graph. So this is a net force against time graph. You determine the area under the graph, you get impulse. But in our level, we don't have the knowledge to do integration yet. So we limit ourselves to a situation where the net force is constant. Okay, if a net force is constant, then our graph won't be that complicated anymore. It will be a straight line. Or we can apply the concept of average by taking this force and finding the average. So if you are able to find an average force, then we can represent this curved line with a straight line. And now the area under the graph will be much more easier to determine. We just take the force average multiplied by the time period. And this area here will be the impulse also. So if we are able to use the concept of average, we can simplify the integration to become a direct multiplication between the average net force and the time period. Or if for that certain situation, let's say you're pushing it with a constant force, then you can also use this equation here to determine impulse, because your net force is constant and it's easier to calculate the area as well. So this is for chapter 3. And when we move on to chapter 5 on work, energy and power, you still do some kind of things which is similar. So for a 1D straight line motion, we are still in straight line displacement. Let's say in the x dimension, we can say the work done by force, this force F here, will be represented by the area under the F parallel x graph. Okay, so you can see we create a new physical quantity. In the rough overview video, I say we create a new physical quantity impulse in chapter 3. So in chapter 5, we create a new physical quantity called work done. And if this work done is work done by this force F, then this work done here is represented by the area under the F parallel x graph. Okay, so I will discuss more what is F parallel now. So if we plot the graph of F parallel against x, then this F parallel here represents the component of F that is parallel to the displacement. I say the displacement is in the x dimension, so I put x dimension x over here. Then in this case, this will be the component of F parallel to the x dimension. So the x component of F actually. So why do I specifically mention F parallel? Why don't I just put F? Because for work done, remember there's a cos theta behind. It's Fs cos theta, right? So we only care about the component of force that is parallel to the displacement. Again, dot product, the idea is parallelness. So we want the force to be parallel to the displacement. So if our force is not parallel to the displacement, we only care about the component that is parallel to the displacement. Therefore, when we plot the graph, we are only interested in the component that is parallel to the displacement. In this case, displacement is in the x dimension, so parallel to the x dimension or the x component. Okay, so at some occasion, if it's a varying force, your component of force parallel to displacement will change with time. Let's say it changed like this. But even if it changed, no matter how, if you determine the area under the graph, this area under the graph will still represent the work done by this force over here. But of course, this equation here, this area under the graph is represented by this equation, and this equation is not within our capability to do yet. So what we do in this chapter 5 here, we limit ourselves to situation where we are able to determine the area. Let's say area of a triangle, area of a trapezium, or area of a rectangle. Those kind of simple geometrical shapes. So let's say if the force is constant, then we can replace it with a constant. Okay, this we are not replacing. It's just that for situation where the force is constant, the graph is much more easier to determine the area under the graph. You can just determine the area under the graph by multiplying the F parallel with the displacement S. And you can find work done is equal to F parallel times S. Okay, so this is a much easier shape to determine its area. Of course, you can do it for a situation where your F parallel is a straight linear line, then you can determine the triangle, or it can be a trapezium shape or rectangle shape. It depends on how the force changes with time. In our syllabus, we won't be dealing with forces that change in such a complicated way. We usually deal with forces that change in the way where the area under the graph is a simple geometrical shape to determine. Okay, so this work equals to F parallel times S. It's not the equation that we have seen last time. Last time we see that work is equivalent to Fs cos theta, but now they say work is equals to F parallel S. Are they the same equation? So let's check it out. So the equation that we learn is F dot S. This is what we learned in the equations part. So let's try and agree with each other, the equations and the graphical, whether they agree each other or not. So let's consider a situation where you have a block, let's say a luggage trolley, and this luggage trolley has a handle over here. So let's say if you pull on the trolley handle using a force F over here, then for this situation, we know that this F here is not constant throughout the motion. Okay, if it's not constant throughout the motion, then we need to determine the work done using a graphical approach. Constant force, only we can use equation. But the idea is this force over here can be broken down into two components. The component that is parallel to the ground, which is parallel to the displacement, and a component which is perpendicular to the ground, which is the component not parallel, perpendicular to the displacement. So you label it by the symbol perpendicular, labeled by the symbol parallel. So we know that only the parallel will be doing work on the object. The one that is perpendicular does no work to the object. So in that case, we don't really care about what's happening at the perpendicular side. We only care about what's happening on the side that is parallel to the displacement. So our displacement, let's say, is in this direction. Then we only take this part. We don't take the part which is perpendicular. So now if we do the calculation to determine the work done, we'll be putting these two arrows here with their tail coincide at one point. So now if you determine the dot product, you just need to find the component of F that is parallel to S. And this component here is F parallel. As we indicate over here, this is F parallel. And we can see this can be determined using F cos theta. So if you know F parallel is equal to F cos theta, now you know that our equation of Fs cos theta here is actually can be rearranged as F cos theta times S. So F cos theta, as you see here, is equivalent to F parallel. So the work done is just equals to F parallel times S. So what are we trying to show here? We're trying to show here that what we learned about the equation in the previous video is actually agree with the graphical approach that I show over here. Okay, so we can determine the work done either through equations or through graphs. If it's through graph, we have greater flexibility. The force can be changing throughout the journey. But for equation, it's only for force that is constant throughout the journey.